So sometimes when we have lots of ions in solution, they start hanging out closer to each other, and they sort of associate instead of dissociating. We think of sodium chloride breaking apart completely to give us sodium ions and chloride ions, and we picture them floating around in solution far away from each other and not interacting. But if you have lots of them, they can start hanging out closer to each other like this, and they can kind of hook up. And so we may not get the 2-for-1 that we're expecting. It might be 1.8 to 1 or 1.9 because a few of those ions hook up. So we have a way to consider this, and we call this the Van Hoff factor. Now, the Van Hoff factor can be calculated from experimental data. So we look at the Van Hoff factor I, and we can calculate it that the I is equal to the change in temperature that's measured in the lab divided by the change in temperature that's calculated, assuming that it is a non-electrolyte, that it does not break apart into pieces. So when we think about this, you would expect for sodium chloride, lithium phosphate, that we would have integers. It's possible to have numbers that are not integers, like 1.7 or 1.5. It's also possible to have numbers that are less than 1. Because just as those ions can hook up in a really concentrated solution, some molecular materials, when they are dissolved, they will actually hook up and make what we call a dimer. Di means 2, mer means unit. So they'll actually take 2 molecules and hook up and dimerize, and when that happens, you can actually have a Van Hoff factor of 0.5, where you don't get the expected result. Okay, so let's look at some of the problems in this unit, and there's a lot of different things we're going to talk about. Let's start off with the easiest. Calculate the freezing point of aqueous 0.237 molal lithium chloride if I is equal to 2. The way I think of this is we take the equation we've been working with, delta T is equal to K sub F times M. And I'm going to add on there, delta T is equal to K sub F times M times I. So what I'm doing is just adding on the multiplication of the Van Hoff factor. And we're going to do this first problem that way. Sometimes I think of Mi as one variable on its own, and we can call this the effective molality. Sometimes it's called the apparent molality. It means the same thing. So we can think of M times I as the effective or apparent molality, which is the number of particles you really have in solution. So let's look at the simplest problem first. The freezing point, well, I know I need to change. Delta T is equal to K sub F times M times I. Since it's aqueous, I look up the K sub F for water, 1.86 degrees C per molal. I look that up on the chart. Times the molality, 0.237 molal lithium chloride, times the I factor, 2. Now, as far as sig figs, I'm taking that for an exact number because by definition there are 2 ions in sodium chloride or lithium chloride. Okay, I'm taking that as an exact number. Down here, this I is from a measured value, so I'm going to use 2 sig figs. But for right now, I'm assuming that's an exact number. And that is equal to 0.882 degrees Celsius, my delta T. So the freezing point is equal to the normal freezing point of water, 0 degrees minus 0.882 degrees Celsius. So the freezing point is negative 0.882 degrees Celsius. Now, this is really important that you remember to subtract, because sometimes I see students just stopping here, and the freezing point isn't 0.882 degrees. That's actually higher than the freezing point of water. So don't make that mistake. Remember to always subtract the difference for freezing point and add the difference for boiling point. Okay, just take a minute at your seats and do the next one.